At some point, most of us have thought about our ancestors and perhaps researched previous generations as far as evidence allowed. But what if we could explore much further? What if we could trace back to the very origin of our species? It is now widely accepted that the dawn of humanity lies in Africa, and modern man's ancestors originated on this continent. To be exact, the birthplace of all new human groups has always been south of a great barrier we now call the Sahara Desert, leading to the phrase sub-Saharan Africa in this context. It was from here that our ancestors colonized the world. However, there are three major issues to consider regarding our departure from Africa and the beginning of a journey that would eventually lead us right the way around the world. Firstly, how many times did we come out of Africa? Secondly, what routes did we take? And finally, is there any way of saying when this occurred? These questions must be answered in order to trace the journey of mankind, because without them, any suggestion regarding the subsequent trails remains speculative. A now widely discredited view holds that groups of our ancestors left Africa over 1 million years ago to make colonies in each of the world's major regions and evolved into separate groups represented today in our so-called races with some degree of subsequent mixture. The multi-regional theory has now been invalidated by both skeletal and genetic evidence, evidence which clearly indicates that anatomically modern human beings, our ancestors, took a more recent exit out of Africa and replaced all other human populations throughout the world. These contrasting views underline the first of our three fundamental questions. That is, how many successful exits out of Africa has modern man made in the past 200,000 years to result in today's diverse populations around the world? There would have been three potential corridors leading us out of Africa. North across to Gibraltar from Morocco, northeast across the Sinai from Egypt, and east across the mouth of the Red Sea from Djibouti. The current climate most likely determined which of the three routes was open at any particular time. Modern humans first left Africa over 120,000 years ago, when the climate was warm and moist enough for the Sahara to become green through an open northern gate across the Sinai. But this was a foray that ended in disaster, as the formerly habitable Levant turned to desert 90,000 years ago. The evidence for this abortive exit can be found in the dated human fossil skulls found in that region. However, there are no dated modern human skulls found there after 90,000 years ago. The Levant was left unoccupied until the climate improved, but because the northern corridor to it remained shut, it was not modern man, but instead our cousin the Neanderthal, who subsequently reoccupied this region by migrating southwards. There is additionally no genetic evidence for survival of this early colony in the modern gene pool. Given that the first modern human exit from Africa eventually ended in disaster, the story of the subsequent exit, as told by the genetic picture of people today, is very revealing and simple. According to Professor Stephen Oppenheimer, it turns out there was ultimately only one successful exit from Africa. How do we know this?
Essentially, it's because there's only one genetic line coming out of Africa. When we're tracing migrations using DNA, one of the best ways of doing this is using DNA which doesn't get mixed and shuffled at each generation. And there are two small parts of our genome which fit this bill. And one of them is mitochondrial DNA, which we all have, but is only transmitted down our maternal side. And the other is the Y chromosome, which only males have. The mitochondrial DNA, which I'll concentrate on, is formed in little organelles in our cells called the mitochondria. They're rather like little batteries which provide the energy for the cell to perform, but they also have their own DNA, and when they divide, the DNA divides with them. Every few generations there will be a mutation occurring in the stretch of DNA in the mitochondria. And we use those tiny mutations as branching points in a tree. So imagine that we start off with one founding female arriving in a particular area. That female will have a particular DNA molecule. After many generations, one of her descendant daughters will have a small mutation and will form a new type or a new line of DNA. And after many generations, then there will be another mutation in one of the daughter lines, and that will form yet another branch. And so you can imagine that if all of these mutations which have occurred in the multiple daughters and granddaughters of our founding female, we build up a tree. So let's put this in the context of the whole human mitochondrial DNA tree, both inside and outside Africa. All the descendant daughters from that single female root are in Africa, and then one of them goes out of Africa. We call that a founder line. In the case of Africa, our founder line that came out was L3. Those founders will then have daughter lines which have mutations which are not found in Africa. They identify these as new growth outside Africa on our genetic tree. We find L3 in Africa, and we also find L3 outside Africa. In fact, everybody outside Africa is descended from L3.
So if the genetic evidence tells us there was only one group and one successful exit, which route did they take? The logical answer can be found by analysing the climatic and genetic clues. As we have said, there would have been three possibilities. The first two possibilities would have required sub-Saharan people to have crossed the Sahara. For the first hypothetical route, north across the mouth of the Mediterranean to Gibraltar and Spain, there is no archaeological, let alone genetic or climatic evidence for it to be a viable candidate. The second hypothetical route, north across the Sahara and across the Sinai, is the most often suggested, but as we shall see, can be more or less ruled out as feasible, let alone the definitive exit, by the climatic and genetic evidence. Dealing first with climate, the Sahara has only been green and open to hunters twice during modern humans' time on Earth, and then only briefly when global warming made a moist climate, evidence of which is found with recent discoveries of ancient rock art, life-size carvings of giraffe, native to a fertile Sahara. The first time was 125,000 years ago, when the Skul and Kavse people made their doomed foray. The second only 8,000 years ago, which is far too recent. But between 10,000 and 90,000 years ago, the only other times we could have exited Africa, the Sahara was at its largest and therefore most formidable, and there was simply no way across it. Logically, this leaves the final possibility. Effectively, there was only one exit from sub-Saharan Africa. That is, across the mouth of the Red Sea. This would have been climatically feasible, as shown by the nearby green refuge of the Ethiopian and Eritrean uplands, which are accessible directly from sub-Saharan Africa, followed by the narrow gap across the Red Sea at the time of a lower sea level, and the green refuge on the other side in the Yemen highlands.
Well, the genetic confirmation, to my mind, that we're looking at the southern route as the definitive exit from Africa, comes from looking at the earliest branches of the gene tree outside Africa. The earliest branches from L3 are M, N, and N's daughter R. And these three primary root branches from the Out of Africa line are found in South Asia and Southeast Asia, and also the oldest evidence of modern human colonization outside Africa are in Southeast Asia rather than and South Asia rather than in Europe.
If that L3 group had just crossed the mouth of the Red Sea and then immediately dispersed, we would expect to find multiple different African genetic lines. In fact, we find just one. This is due to genetic drift. From time to time in each generation, some mothers' lines will die out because they have no daughters surviving to reproduce. In a small isolated population, such as the initial founding line into the Yemen, a single surviving ancestral line predominates. Genetic drift also confirms the one successful exit. Had there been multiple exits, over time there would be greater genetic diversity outside Africa, rather than the single L3 genetic line which exists today. In summary, only one small twig of one branch out of the dozen major African maternal clans available over 60,000 years ago survived after leaving the continent to colonize the rest of the world. From this small group evolved all modern human populations outside Africa. This is the critical point, the simple and singular fact that only one African line accounts for all non-Africans. A southern route across the Red Sea, which is most accessible when the Earth is glaciated, goes some way to explaining the mounting evidence for our own defining exodus from Africa. But are there any clues as to exactly when this exodus took place? And if the mouth of the Red Sea was the exit, why had we not used it much earlier? One problem is that genetic dates are only approximate, with a wide error margin. Whilst the gene tree tells us there was only one successful exodus, the limits of the approximate genetic age of the single Out of Africa branch, L3, allows that this could have taken place any time between 70,000 and 95,000 years ago. Our ancestors would have been beachcombing from at least 125,000 years ago, when the first shell middens are found on the western coast of the Red Sea, before deciding to move on. Thus, they could have been waiting anything between 30,000 to 55,000 years at the Gate of Grief before starting on the beachcombing trail, although the sea level was probably low enough throughout that period to allow people to cross exposed reefs to the other side with the aid of rafts. In order to narrow this event window another way, we must examine both the archaeological and the geoclimatic evidence. The archaeological clues are thinly scattered, since the beaches our ancestors wandered along are now 100 metres below sea level, and they're mainly found on the other side of the Indian Ocean. Measurements made on the Greenland ice cap show that the second coldest time of the last 100,000 years was between 60,000 and 80,000 years ago. At its coldest, 65,000 years ago, this glaciation took the world's sea levels 104 metres below today's levels. The way in which this sea low stand, as it is called, was measured in the Red Sea holds an unexpected clue for what might have been the stimulus to move. Oceanographers have been able to measure interglacial sea level high stands by looking at coral reefs. Sea level low stands, however, which occurred during glacial maxima, are more difficult to confirm. Elko Rowling, an oceanographer at Southampton University, has found a way to use the Red Sea to overcome this problem. He measured prehistoric levels of Red Sea plankton. During full or maximum glaciation, sea levels are so shallow that the Gate of Grief approaches closure, and the Red Sea becomes effectively isolated from exchange with the Indian Ocean. Evaporation causes the Red Sea salinity to increase so much that plankton, the base of the marine food chain, disappears. Notably, one particular highly sensitive species of plankton started to decline severely 85 to 90,000 years ago. The low level of plankton allowed oceanographers Rowling, Siddall and colleagues to estimate 80 metres for the sea level depression at this time. Low levels of plankton in the Red Sea would have affected the food chain and the success of the beachcombers there. By contrast, the beaches of the Gulf of Aden, just across the water in the Yemen, were outside the Gate of Grief and had nutrient-rich, oxygenated upwelling water from the Indian Ocean. In other words, a few kilometres over, on the southern Arabian coast, the beachcombing conditions were probably excellent. So perhaps dwindling food resources on the western shores of the Red Sea, attractive beaches on the Gulf of Aden, and cool, wet Yemeni uplands for refuge were what spurred our ancestors to take their momentous step nearer 85,000 years ago, rather than during the next cold period of even lower sea level 65,000 years ago. The next geoclimatic clue to the date of our exit is suggested from cores drilled in the Arabian seabed. Cores that reveal the extent of the volcanic eruption of Toba in Sumatra 74,000 years ago. Known to be by far the biggest eruption of the last 2 million years, this mega explosion caused a prolonged nuclear winter and released ash in a huge plume that, from the evidence of the sea cores and ash falls on land, spread to the northwest and covered India, Pakistan and the Gulf region. The Toba eruption is thus a valuable date and geographical marker, since the ash covered such a wide area, is accurately dated, and can be identified wherever an undisturbed layer of it is found. How does the distribution of the ash help us? Archaeologists in India have started to look at cultural and fossil evidence for modern humans both above and below primary Toba ash layers. Their findings are beginning to support the view that our ancestors arrived before the Toba event. There are genetic clues as well. If our ancestors left Africa 80,000 years ago, their descendants would have anticipated the Toba explosion in Sumatra by 6,000 years, and the beachcombers in India would have been in most direct line for the greatest volcanic ashfall in the whole of human existence. The sharp genetic line dividing India and Indochina could be interpreted as the scar left over from that world-shaking event. On the Indochina side of the ashfall, Malaysian archaeologist Zorena Majid has explored the remains of a modern human culture in a wooded valley in Perak State near Penang on the other side of the Indian Ocean. A continuous Paleolithic tradition known as the Kota Tampan culture goes back tens of thousands of years there. At one site, tools from this tradition lie embedded in volcanic ash from Toba. We will look at the significance of Toba later, but if the association with modern humans is confirmed, this means that modern humans got to Southeast Asia before the Toba eruption, more than 74,000 years ago. This in turn makes the 80,000-year-old exodus more likely. So rather than an exodus through the Sinai, a small group of people may have crossed the mouth of the Red Sea about 80,000 years ago, using rafts to island hop, reef to reef, over the 7-mile stretch of water as the founding population for all modern non-Africans. Finding themselves on a new continent, our ancestors would almost certainly have been restricted to the coastline. Apart from the nearby lush Yemen highlands, heading inland to the Arabian desert was not an option, but the South Yemen coast would have provided a supply of shellfish and other marine produce, and there would have been fresh water seepages from the ephemeral wadi systems draining seawards all along the beaches. Our ancestors tried to explore new lands beyond Africa twice. Both exits succeeded, but not both expeditions. We can see only one group of people coming out of Africa over 70,000 years ago. This fundamental departure from the conventional view of multiple movements out of Africa fixes all subsequent migration routes for the rest of human history, starting from that single southern trail. So we had left Africa. Where to now? If we didn't know where we were going, why did we follow the parched coastline, beachcombing as we went? How could we know it was a successful form of existence, notwithstanding its limitations and restrictions, and that greener pastures lay beyond the Arabian Peninsula? The journey, our journey, was just beginning. In the forthcoming films of the Stephen Oppenheimer Journey of Mankind iLecture series, learn how our ancestors beachcombed their way along the southern coast of the Arabian Peninsula towards India, followed by the rapid spread along the coast into East Asia. How the eruption of Mount Toba 74,000 years ago obliterated the first colonies in India, and how during the recovery that followed in South Asia, Australia was also colonised. Moving again, see how, when and why we colonised Europe relatively late, then to the time that the last ice age gripped the planet, forcing the human population to lower latitudes. And the most distant leg of our journey, from Siberia into Alaska, where our ancestors entered the Americas. From a single successful African exodus, all of the world's continents had now been colonized.